right, in this work example, we're going to be going over some of Newton's laws of gravity questions. A Newton's law of gravity question. It's one question, but it's part A, B, C, D, E, F, G, as usual with these types of questions. So state Newton's law of gravitation. Newton's law of gravitation says that the force of gravity between two, let's call them point masses, is directly proportional to the product of the masses. The more massive, the more gravity. But the force of gravity is also inversely proportional to their separation distance squared. So we put all those ideas together, we could say the force of gravity is directly proportional to the product of the masses, 2 point masses. The force of gravity is inversely proportional to their separation distance squared. Turn that into an equation with a constant of proportionality, and we get this familiar Newton's law of gravitation. It's good to be able to explain that in words like this. So 2 marks there. If you need any of that for a moment or two longer, go ahead and pause the video now. Question goes on to read, the planet Jupiter and one of its moons, Io, may be considered to be uniform spheres that are isolated in space. That's the idea of a point mass. Jupiter has radius r and mean density rho. Io has mass lowercase m and is in a circular orbit about Jupiter with radius n r. All right, so they're expressing the distance to Io in terms of the number of Jupiter radii. So Jupiter has a certain radius, and Io is a number of those radii away. The time for Io to complete one orbit of Jupiter is t. Show that the time t is related to the mean density rho of Jupiter by the expression. So the time it takes Io to orbit is related to the density of Jupiter. Okay. We saw calculation very similar to this, considering our moon around the Earth, right? And so this was a practice calculation that we had done. And I thought when we did it, oh, I'll give them the Io Jupiter quiz to see if anybody was able to sort of relate those two. And so an open note quiz, hopefully we found some success on this. Let's lay out all the ideas here very carefully. And by the time we're done, we should get to that thing down there. We want rho t squared on one side. All right, so let's, it's kind of easier for me to make sense of it up here with the figure. So here's what I know about Io going around Jupiter in time t. I know that this is a mass, and I know this is a mass, and there's going to be a force of gravity between them. Jupiter's velocity would take it off this way. Okay, I'm sorry, Io's velocity would take it off that way. Let's say it's going around this direction. In order for it to be in orbit, there must be a centripetal force, right? Pushing it towards the center. And that centripetal force is just telling us the direction towards the center of the circle. It's provided by this force that I just mentioned, gravity. So a centripetal force is this mass times its velocity squared over its radius from the thing it's being, it's orbiting. And they've defined that here as nr. So be very careful about sort of how you're substituting into sort of the familiar equations, mv squared over r in general, but they've defined this r, the radius of its orbit, as nr, where r is Jupiter's radius. So that's the centripetal force that's sort of pushing Io towards the center of Jupiter, and its inertia sort of forward allows it to orbit. So that is provided by gravity, the one we just talked about up there. how far apart they are, squared. So we set those equal to each other because gravity is providing the centripetal force. It looks like we can cancel out this, that, and one, n times r would be n squared r squared. So like one factor of nr, can cancel out. We still have nr on this side. So we get v squared. This is our orbital velocity equation, right? Io, just like anything in orbit, has to have a certain speed at that distance to maintain its orbit. Gm over n capital R. Here we can make a substitution. I'm going to sort of go half an orbit later. Here's Io, just so I can kind of work on this side. And so now Io has made it here. It's sort of its velocity is like this. And what is velocity? Distance divided by time. Miles per hour, meters per second, light years per century. Any unit of distance divided by any unit of time is a velocity. The distance around a circle is going to be 2 pi. And again, the radius of this circle is nr, 2 pi nr. Divided by time t, they define the time it takes to orbit as this capital letter T. So that's what velocity is. Velocity squared is equal to this. What's velocity again? 2 pi nr over T. This equation says that velocity is squared. All right, alphabet soup for breakfast here. 2 times 2, 2 squared is 4. Pi squared is about 9, but we'll just leave it like this. Pi squared. We got ourselves n squared r squared over t squared equal to m over n r. Now, right away, how's that pi gonna cancel? See how we have pi squared? Oh, okay, we still got more work to do. Note how there's no m in this equation, right? We got an m there, but there's no m in that equation. So we're gonna have to do a little bit more work. I was worried about this, like, oh, pi squared. Oh no, we have to think through this a little bit more clearly. So rho, density, in general, is just mass per volume. Okay. We want to know the mass of the planet Jupiter because it's capital M. It's the thing being orbited. So that's, this. Let's rewrite this equation as mass equals rho times volume. Okay, that's how we'll introduce rho into this. And this is how we'll get rid of a pi, because what's the volume of a sphere, right? They said that we can assume that Jupiter is a sphere isolated in space. So now we've got the mass of Jupiter equal to its density times the volume of a sphere is 4/3 pi. And now here we're just using r because they said the radius of Jupiter is r, and it's, the sphere that we're sort of getting the volume of. And so it's not nr, that's the radius of the orbit of its moon Io. Here we just want capital R. So 4/3 pi r cubed is the formula for the volume of a sphere. So we need to substitute all of this in here for mass into this equation. Let's see what that's going to look like. Ooh, it's going to get worse before it gets better, that's for sure. All right, so let's do G times M, but M is rho 4/3 pi r cubed. So that's GM on this side over NR equal to 4 pi squared n squared r squared over t squared. I'm going to copy that down on my whiteboard here. G rho 4/3 pi capital R cubed over NR equal to 4 pi squared n squared r squared over t squared. Everybody got all that? Good. Give myself a little bit more space here to work through it. So if you didn't follow all that, just hit pause, rewind the tape a bit, get it all down, and then rejoin us when you're done. We got G, rho, 4/3, I, R cubed over NR equal to 4 pi squared, n squared r squared over t squared. Now we want to get this term on one side. Okay, so there's our rho, there's our t squared. So it's kind of like the first thing I would do is just multiply both sides by t squared. So now I've got my rho and my t squared sort of on the same side of the equation, and I just got to get rid of all this other stuff on this side. Let's go ahead and see that this is going to cancel sort of one of those. Remember, r cubed is r times r times r. So now it's only r squared, right? If I get rid of that one. All right, so now we've got t squared. I'm going to put this rho right next to it like this, right? Nice and neat like that. So that's that rho times t squared. And what all the rest do I got here? I got a g. I got a 4, let's do it like this, 4/3. I got a pi up there in the numerator. I got an n down here in the denominator with that 3. And I got an r squared up there still. All right, so 4/3 pi, and all that's equal to everything over here, 4 pi squared, n squared, r squared. Now let's get rid of all of this. So to get rid of this term right here, let's just multiply by 3n over g 4 pi r squared. Same thing over here, 3n over g 4 pi r squared. Those 3 n's will cancel. G times 4 cancels. Pi squared cancels. I got my rho t squared equal to. Now it should be all this when we're all done. Let's see. There's our g in the denominator. That's good. A 4 is going to cancel. A pi is going to cancel. I always hate canceling pi. R squared is going to cancel. And we got this n and these n squareds to be an n to the 3rd. Got a pi left over here. At least one pi is left over. Still got a factor 3. 3 pi n cubed over g. Check, check, check. We got it. All right, that's that. That's all it takes. 4 marks. Easy come, easy go. Now, that's not easy, guys. That's pretty tough, right? We're doing some astrophysics here. And now we're going to calculate the mean density of Jupiter from all of that. So even if you couldn't show sort of why that was true, you can trust that the test isn't going to lie to you. Rho t squared is equal to, what was it? 3 pi n cubed over g. My memory serves me correctly from a moment ago. Okay. So now we're going to use this to actually calculate the density of Jupiter. So let's get rid of that t squared, put it back over here. All right, now we got rho all by itself, and we just make some substitutions. So we got to calculate n first. Okay, we know that the radius of Jupiter is r, and the distance from Jupiter to Io is n times r. So if we do nr and we divide the radius of Jupiter into the radius of Io's orbit, then we'll cancel out the radius of Jupiter, right? So then we'll know what n is. So we know what the value of the radius of Io's orbit is. It's given here. It's saying the distance between the center of Jupiter and Io is this. And so that value, nr, is nr equals 4.32 by 10 to the 5 kilometers. The radius of Jupiter itself right? That we want to divide into that, like how many Jupiter radii is this? We don't care about sort of the radius of Jupiter. We just want to know how many Jupiter radii to get to Io. The same thing we're doing with our scale models. We're saying how many moon diameters to get to the Earth. You know, it's 120 moon diameters to get to the Earth. That would be n for that. So this one is going to be the radius of Jupiter, 7.15 by 10 to the 4 kilometers. Kilometers are going to cancel, so it's okay to leave them in those units. We'll take that ratio first. 4.32 times 10 to the 5th divided by 7.15 by, figure that out, 4.32 by 10 to the 5th divided by, open parentheses, 7.15 by 10 to the 4th. And so this number is about 6. Okay, it's about 6 Jupiter radii. If you got the Io, it's like 6.04. I'm just going to call it 6. And I guess we'll keep it. All right, so rho is going to be equal to 3 times pi times 6.04 cubed over g times t. Takes 42.5 hours for Io to orbit. Times 3,600 seconds per hour. Where that? 6.04 to the 3rd power times pi times 3 equals 2,078. I get for my numerator divided by g, 6.67 by 10 to the negative 11th. And then divided by, open parentheses, twice, 42.5 times 3,600, close parentheses, squared, close them again, equals, I get 1,331, which I would just maybe say 1,300 kilograms per cubic meter for Jupiter. Now it says Earth has a mean density of 5.5 by 10 to the 3. I think that's what we actually calculated a few weeks ago. And we did this similar calculation using the Earth and our moon. It's said to be made of rock. That's what it said, you know, for this hypothetical Earth planet they're referencing here. It is said to be made, you know, a planet made of rock, you guys. By reference to your answer in 1, comment on the possible composition of Jupiter. And here you might recognize that this number is a lot lower than this number, and so it's less dense, and therefore probably not composed of the same material rock. We kind of know something about Jupiter maybe in this class. Oh yeah, it is a gas giant. But we can't really, you know, conclude that just from this. We could say, because the density is lower, it suggests it's composed of something with much lower density, like a gas. You know, you can kind of reason your way to that, right? So a takeaway from this is that we can relate the density of a planet to what? The time that it takes one of its moons to orbit based on how many radii of that planet it is away. With a telescope, we can see how big Jupiter looks through our telescope, right? And we don't have to know really how big it physically is. We can just say, look, to get over to that dot there, Io, it takes 6 of Jupiter's sort of radii to get over there. And that's all we need, right? And then we just sort of time. How long has it taken this planet to go back, you know, to go around? You just observe it for 42.5 hours and it's back to where it started. And that's enough right there to say, well, how dense is this planet? And that's very profound. It should be lost on you how the sort of scientific reasoning here leads to powerful conclusions. This has been another quiz with Dr. Schleich, and we'll see you next time.